Hi all, I'm Pandigital, and if you didn't already know, I'm a big fan of Pandigital Numbers. But numbers come in all shapes and sizes, of course, prime numbers and square numbers and so on. And over the years, I've had a bit of fun looking for ways to link them to my favourites, the Pandigital numbers. Take, for example, the RepDigit, or monodigit numbers as they're sometimes called. Now, in a way, these numbers and Pandigital numbers are complete opposites, because whereas one contains each of the digits once and once only, the other contains just one digit repeated, well, as many times as you like. But despite the difference, there's still lots of ways you can link them together. For example, you probably already know that the sum of the first 9 repunit numbers gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, a 0th Pandigital number. And it's well known that the squares of those numbers gives a series of palindromes where, in the last one, the head and the tail both contain the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. I admit that it's a bit annoying that the digit 9 in the middle has to be used twice to make this work, but you can get around this by taking the product of the consecutive repunit numbers. And again, you end up with a palindrome, but this time the head and the tail are separate Pandigital numbers. And you can go from a Pandigital series to a RepDigit series in several ways, but I'm not going to waste your time showing you lots of patterns you've probably seen countless times before. After all, you can construct lots of these patterns yourself. You may wonder, for example, whether the sum of the self-descriptive RepDigit numbers is Pandigital. What do you think? Sadly, it isn't, but it's pretty close. Only the 2 and the 4 are missing. So then, you may wonder whether it's actually possible for any series of distinct RepDigit numbers to add to a Pandigital number. Now, that is possible, and in fact, it won't take you too long with a bit of trial and error to find out there's thousands of ways of doing it. I'll leave you to work out how many, but it's a lot. Here's 2 ways it can be done using 10 distinct RepDigit numbers, but it can be done with as few as 6 in some cases. These 2 are quite interesting because the numbers can be arranged in a nice triangular shaped pattern. And this triangle is really interesting because all the numbers shown in red contain odd digits and all the numbers shown in blue contain the even digits. There's only one other sum like this and, well, see if we can find it. Turns out there's more than 45,000 sums that lead to Pandigital numbers, and several of them can be reached in more than one way. Here's 2 with an equal sum, and the Pandigital number on the right can be made from the sum of RepDigit numbers in 132 different ways, which is the most possible. Now, I'm aware that some people find numbers on their own a bit boring, so something I like to do is to try and construct patterns out of them. Here's a rather nice way to arrange the set of 6 equal sums. It's a type of magic hexagram, which is a 6-pointed star, where each row contains distinct RepDigit numbers and they all have the same sum, which is Pandigital, of course. Here's a heptagram, an octagram, and a nonagram that have the same property. For the larger patterns, I realised that there's more than one way to arrange the rows, but this arrangement has beat me. I can only get 8 of the 9 rows to add up correctly. Maybe you can do better, I don't know. Multiplication is another good way to link RepDigit and Pandigital numbers together. There's only one zeroless Pandigital number that has RepDigit factors, but there's many that are doubly and triply Pandigital, and I think there's probably many larger ones too. But you have to be careful when making claims like this because digital patterns can be very frustrating. It's easy to jump to conclusions. For example, we saw earlier that this product can be split into 2 groups of zeroless numbers, and here's another that can be split into 2 groups containing all 10 digits. So the question is it possible to split larger products into groups of 10 digits? I don't know, I can't be sure. This one comes really close, but if you look carefully you'll realise that the 2 and the 5 are actually the wrong way round, which I find seriously annoying. And in this one, the pair 5, 4 and 4, 5 are the wrong way round, so I don't know, maybe it's not possible. There are others, such as these, where the middle of the product is also Pandigital, and I find these 2 particularly fascinating because, well, I'm just amazed how 3 numbers which between them only contain 2 distinct digits transform via a sort of 5, 10, 5 digital template into a doubly Pandigital number which contains another right in the middle. And this one contains a sequence 0, 9876, 54321, in the middle of the Pandigital number 45678900123. And finally, there's only 6 fully Pandigital numbers that have RepDigit factors, and from these, 3 can be arranged in a nice triangular shape pattern such that the product of this, this, and this gives this, the product of this, this, and this gives this, and the product of this, this, and this gives this. Quite pretty, I think. I said I like patterns. So there you have it. Time to say cheerio, but please feel free to leave a comment if you know of any other patterns you feel I should have included. As always, I'll leave you with the answers to the questions I posed in the last chapter. Thanks very much for watching.